So yeah, thanks for the chance to talk to you folks about some of our work we've been doing to look at how well we can forecast solar radiation storms. Particularly, I work for NOAA Space Weather Prediction Center, so for us that's a very important part of what we do. Radiation storms are a major component of space weather. So these are particles that are accelerated in solar flares close to the sun, or in shocks that are propagating ahead of coronal mass ejections. And the SEP events, when we see them, like, they mainly consist of energetic protons that are being accelerated in these events. And from these sources at the sun with the flares or the coronal mass ejections, these protons and other particles can be propagated throughout the heliosphere, sort of in line with the magnetic field. And so if you are sitting here at Earth, for example, you would expect to see a lot of proton events for sources that you're magnetically well connected to. And thanks to the Parker spiral, that means we're seeing storms that are occurring on the western hemisphere of the sun, and coronal mass ejections are coming off from the western hemisphere. We're really well connected to those events. And so we tend to see a lot of energetic particles from those events, but not just necessarily from those regions. We also see things from like the center disk and eastern hemisphere. And when those storms and those particles can reach us here at Earth, they can have quite bad impacts for things like satellites in terms of degradation and causing upsets in terms of what the electronics are doing. They can cause problems for the aviation industry through elevated radiation levels for high-flying aircraft, especially over the poles, and also for astronauts in space. For the whole human space exploration industry, that's an important factor. You want to know when these storms are coming to protect your astronauts. And then also for things like high frequency communications, for especially over the polar regions, when these protons are hitting us here at Earth, they can alter the D region of the atmosphere and really upset the high frequency communication and degrade those signals up in those polar regions. And SEPs and those protons, especially when we're magnetically well connected to them, those particles can be at Earth within tens of minutes after a flare or a CME leaving the sun. So for us, that's a real challenge for us to forecast these events and to give our customers in the satellite aviation industry, etc., to give them warnings and forecasts with enough lead time that they can react to that. And so we've been going back and looking at the last two solar cycles. So this is back to 1996. All the way through to 2019, looking at those last two solar cycles and trying to see, well, how well did our forecasts and our warning products actually perform, and putting this together in a format that can be provided to the research community as sort of a benchmarking for future model validation, and as new models, both physics-based and machine learning and empirical, all these models as they're being developed, to give the people a benchmark for, here's what we can do in terms of our forecasting, and we'd love to see new methods and new techniques to improve that. And so if anyone's interested, that result is now just out in a paper this year, if people want to dig into the details. So to give you sort of a quick overview of what we do at SWPC, for radiation storms, we basically have two kinds of products. We have our short-term products, which typically give you something along the lines of like minutes to an hour warning before an event. These are called our warning and alert products. And we have our 3-day probabilistic forecasts, which are giving you a forecast for day 1, day 2, and day 3 into the future. And so these are typically based around the GOES, well, not typically, they are based around the GOES particle measurements from the GOES instruments up in geostationary orbit. And so the GOES particle instruments are recording protons here at 10, 50, and 100 MeV. This is the 3 colored lines here on the left and on the right. We tend to communicate the intensity of a storm in terms of what we call the S scale. This let me see, where's my cursor? The S1, the S2, and S3 scales. So that's specifically when this red line here, which is 10 MeV, crosses the threshold for particle flux units at the S1 level, the S2, and then at the S3 level. And so what we're trying to do in our warning and our probabilistic forecasts, well, specifically, let's start with the warning forecast. We're trying to give you customers a warning of when we expect this red line to cross this black dash line. So that's the 10 MeVs. And then also for when 100 MeVs crosses the 1 PFU line. So that's this green line crossing this dotted line down here. And so what we'll try and do is get a warning product out first, and then that will tell customers that we expect that something is imminent. We're pretty confident that it's coming, and it'll be sometime in the next minutes to hours in the future. And then what we also do is follow up with an alert, which is this vertical line here, which tells a customer when that threshold has actually been crossed. So obviously for us, we would love our warnings to come before our alerts, which means we get our forecast out ahead of the event actually happening. And we do much better in this short-term mode where we can sort of predict something an hour or a couple of minutes to hours in advance. But for whatever reason, I decided I would concentrate on the probabilistic forecasts today, mainly because I think that we can dig into some more interesting validation techniques for these forecasts. And so this is, with our probabilistic forecasts, we're looking at this S1 level. But instead of giving you a minute or an hour warning, we're trying to give people this forecast for the next 1, 2, and 3 days. And so this goes out with what we call our SGA forecast, and it goes out at sort of 10 p.m. On one day, and it's valid from midnight of the following, of that night for the next day and the following 2 and 3 days. And so this is specifically when this S1 storm, this red line is going to cross this dash dot line. And so this is probabilistic, whereas this thing on the left is deterministic. And so what we see a lot when we're looking at forecasts and we're looking at model results and stuff is we tend to throw out a lot of numbers. You get things like talking about, your true positives, your false positives, your misses, your false negatives. We talk about our probabilities of detections, our false alarm ratios. We talk about our skill scores, like hide key skill scores and the true skill scores. And this is all great. But you can definitely, dig in some of these numbers and see, for example, just pulling a few things here, like our probability of detection, so our ability to detect events when they happen, between these two solar cycles for day one increased from 47% to 62%. So yes, that's great. You can see there's an increase there. You can see our false alarm ratio, unfortunately, went up a little bit. Generally, you can see our skills went up a little bit. And that's great. It gives us a nice number to base this on, but it's not digging far enough into those results from a forecaster's perspective to be able to understand how they would use this in a real-time operational setting. So it's great as a benchmark, but what I want to talk about is to think a little bit deeper about how we present our model results and assess a model's weakness and strength in terms of how we communicate that to people who might use our models. And so actually on this previous slide, this was just a quick cut through a probabilistic forecast here. This was using a decision threshold of 50%, and it was just then labeling the forecast as deterministic. Did we get it right? Did we get it right? If it was greater than 50% and an event happened, that was a yes. If we had a probabilistic forecast of less than 50% and we got it right, that was correct. It was a correct null. And did we determine whether the event happened or not at that 50% level? But not all forecast users are actually interested in that 50% level. Certainly NASA, when they're looking at the astronaut health, they will start to get interested in the probabilistic forecast when it starts to go above sort of 7%. That's them sort of starting to get interested in what might be happening. Once it starts getting above 20%, for them, that is something of reasonable concern that they would want to think about whether or not they would take action on astronaut safety or preparing for them to return to shelter. And so it's really important for us from a forecast perspective to display these forecasts in that probabilistic sense to convey that uncertainty in the forecast. If we had just taken this 50% split here for the day 3 forecast, we would have totally missed the fact that there's this bump in the false alarm ratio, which shows the false alarm ratio increases around about our 80% threshold. And I'll dig into that in a little bit more detail in the next couple of slides. So one thing we can look at is reliability and attributes diagrams. These are showing our forecast probability versus the relative frequency of an event. And a well-calibrated forecast should lie along this diagonal line here where it's reliable. And that's saying if you give a forecast of 60% probability, then it should occur, then the event that you're forecasting should occur 60% of the time. And so this is each of our forecast probability bins. You can see to these points here. And generally, you can see that things in this situation lie along the diagonal. If you were under the diagonal, then you're over forecasting. And if you're over the diagonal, then you're under forecasting. And so that gives you an idea of how your forecasts rely compared to how often an event actually happens. However, even the most perfect forecast might not rely on that perfect diagonal line just because of counting statistics. And so we can try and show that here by adding consistency bars to those points, which shows how far from that diagonal you can deviate and still have a reliable forecast. So if you're interested in knowing more about this, this is based on a resampling technique from the Brocker and Smith. But basically, from understanding the results, if you're on these gray consistency lines, then you are still within the bounds of a reliable forecast. And also shown here is our climatological no resolution line. So this is saying that for each solar cycle, whatever, there's a particular event rate which shows you the number of days. This is like less than 1 day in 30 has a proton event. And so you could forecast continually just the climatological event rate, but that's not going to be great when there's actually something that's happening. And so what you actually want to see is your forecasts lie away from this no resolution line, and that gives you the ability to discriminate between events occurring at different relative frequencies. And so this is our results for solar cycle 24, split into our day 1, day 2, and day 3 forecasts. And generally, you can see that most of our forecasts lie on these gray consistency bars, which show that they're, for the most part, reliable. However, there are a few parts in these plots that show that actually our forecasts deviate from that reliable, from a perfectly reliable system in some way. So that's the first one is down here in our day 1 forecast. You can see that we're over forecasting in this sort of 20 to 30% range. And it was interesting, I spoke to our forecasters and their interpretation of that was that this could be occurring for active regions that are on the backside of the sun. So something that's perhaps on the eastern limb, we can't see it yet with those with our observations of what the magnetic field looks like in the active region that might produce the flare of the CME. But you know, perhaps from stereo, which is an instrument which is around the limb, that you're seeing something in ultraviolet, extreme ultraviolet. So you know something's there, but you don't know the complexity of it. You don't quite know whether you expect it to erupt and cause a big proton event. And so what they said there was that this perhaps this over forecast here was based on trying to give a customer sort of a heads up of, hey, something's happening. We're not going to say that it's definitely going to do something yet, but there's something happening. We want you to be prepared for that. And so that was kind of an explanation for here. And then over here on our day 3 forecast, you can see we've got what looks like a big over forecast in the sort of 80 and 90% region. And actually, when you look into the numbers, and this shows you the number of events in each forecast bin, out here in this sort of 80%, 90% level, we've only got about 9 event days throughout the whole solar cycle that are causing this over forecast. And if you were to actually go and look at those, at the data for those events, I think that really there's no erroneous forecast there. These forecasts are made 3 days in advance, and often you don't actually know what it is that is coming 3 days in advance. You don't know if it's going to be a big event that continues and lasts for several days, or you don't know whether it's going to turn over and sort of fizzle out after one. And what's happening here is perhaps a forecaster is saying to the customers, hey, something is, like there's a lot of stuff going on in the sun. It may well last a long time. We've seen an active region, it's been popping off events for the last few days. That activity might continue. And in some cases, what it might be is that the event just finished an awful lot earlier than what they expected. Usually these events have a nice smooth decay. And in some of these cases, you can see it just precipitously dropped in a way that you wouldn't really anticipate based on how you would forecast. So these are two situations where, you know, this one is perhaps not really an erroneous forecast, but this here is something that we can actually maybe correct. And maybe we need to get observations that could correct this over forecast down here. Or maybe it's good that maybe the customers do want to know if something is coming and they do want to know it's a low probability, but they do want to be prepared. And so those are two sort of examples of how we would dig into that forecast and communicate that to our customers. And it's important to know where our tendencies tend to be and where we're over forecasting or under forecasting. I'll try and not spend too much time on this because I don't want to go over too much on time, but so far all of that forecast validation has been considering one day as sort of statistically independent from the next. But we all know that if it was rainy yesterday, there's a good chance it'll be rainy today. And so this is the same with proton forecasting. Persistence plays a huge part in our ability to forecast. And so what we wanted to do was to try and look and see, well, how good are we actually at forecasting sort of 2 days, where at least one day of those days has an event going on. And so you can split the time profile up into these 3 days. So let's just look at day 1 and day 2. On this day one, nothing, we were not over the threshold, so this would have been a no forecast. And on day two, we are over thresholds, this would have been a yes forecast. So for the onset of an event where you would go from no event to event, you have four possible things that you can forecast for those 2 days. You could say, yes, yes, there's going to be events on both days. Yes, no, there'd be an event on the first day, no event on the second day. The correct forecast, which was no on the first day and yes on the second day, and then to complete the set, the no, no. So obviously for this no event transition to event, there is a perfect forecast, no to yes. We can then expand that so we know that that's a correct null and a hit, and we give these some labels, so you'll see why in a minute. But we can expand it to different portions of the event. So once you're during the middle of an event, you would see this hit, hit, yes, yes. And then at the end of the event, a perfect forecast would be a yes to a no, where you're going now below threshold and you've got a hit and a correct null. And so taking all this information, and this is going to be way too much information for the time that I've got, we can basically display this on a radar plot, and it shows our ability to forecast these different portions of the storm. And so I'll not dig into the details of this, there's a lot to go into, but it's a different way of looking at that forecast to be able to understand how well we do at different portions of the event. The answer is not so well at the start. We do not do well with the correct forecast of 24 hours in advance, being able to forecast the onset of an event from nothing happening to something happening. You can see basically we didn't get any of those correct. And so that's something that we realize we need to work on in the research community, is understanding the triggers for these events in advance to be able to give a better lead time on those forecasts. And so I'll skip those two and just leave it there and say that while there's a lot of details to go into, and if you're interested, go and see the paper, but it sort of summarizes our current forecast capabilities. And what we're trying to do is provide a benchmark to people developing models and applications for them to look at their models and compare it to those results. And it might be that a model doesn't solve the whole problem all at once, doesn't solve everything or understand everything about the solar proton problem, but maybe if we can improve the start of an event and our forecast there, maybe if we can improve our ability to forecast 3 days in advance, then we're moving the problem forward and we're getting better at those forecasts. And I think this just shows the importance of pairing metrics and skill scores with data in the context of data and what is happening and what we know from our general scientific understanding. And so I threw out a couple of discussion questions, and I think this applies to not just machine learning, not just to physics-based models, but to the whole community. Can we do more to dig into the results produced by these models to sort of really understand their strengths and their weaknesses? Can we do more to communicate those models' strengths and weaknesses and provide measures of uncertainty and ambiguity? And does the research community need more details about how customers use those forecasts in order to understand how their model would be used when it would be implemented operationally for forecasting? And so I will leave it there and see if anybody has any questions.